place where I was ready to take calculus, and I also came back to higher education as a non-traditional student after about 4 or 5 years away from high school, after I had worked as a journalist for a few years. So I say all this to say that when people think of people who are good at math, they might think of someone who did like who was in math contests or could calculate things quickly, and I was not any of those. I would say that one of the things I do well is working with mental models of things, and looking at some different mental models of math has helped me a lot. There are two mental models that I always find helpful to share at the outset. The first is called the rule of four, which is a way of thinking about how we represent mathematical concepts. And it's not just four, it could be more than four. But the idea behind the rule of four, which to my knowledge was originated by Deborah Hughes Hallett and her co-authors in one of their calculus books, is that there are multiple ways to represent mathematical ideas, which are usually set up as graphs, numbers, words, and symbols. And that the more of these you can use and link together, the greater likelihood you have of making your ideas understood. And also, I would say, of effectively solving problems later. So for the sake of efficiency, lots of times things are highly symbolic and highly compressed. But the more we can decompress, kind of unzip those equations and expand them out into experiential understanding and multiple representations, that usually seems to add a lot of value to people's experience with math. And one of the most destructive things that sometimes happens to people is they are pressured to compute quickly in a way that makes their self-worth seem as if it is at risk if they cannot do so. And that is usually what turns people off from math. Most people can remember the moment where they, or I would say many people can remember the moment where they stopped liking math. And so if we can just go back to before that time and work around it, it seems to work pretty well. The other major concept that I like to use, which is not math specific, is, well, let me stop there. Is there anything, y'all have any thoughts on that?
I agree with a lot of people get turned off of math based on personal experiences, maybe with an instructor or just hitting a wall with the concepts or not being fast enough, things like that. I can recall so many kids in school who are like very intelligent, but then they hit a subject like it was math or chemistry, and then the way the instructor taught and their reaction to their struggles just turned them off from the subject completely.
And we don't have to do that. That's like we're not on that path that has an objective like a traditional school is. So we can look at all the different ways we could approach this terrain and each find our own part of it and how we traverse it, which is what's so exciting to me about being a mathematician and a pedagogist, professor, or whatever, outside of that setting where it's in a linear, objective oriented way. Um, the other cognitive tool that I really find valuable as a high level thing is not math specific, but it is about teaching. But it's useful in lots of other contexts outside of teaching. That's this idea of Bloom's taxonomy. This is something I used quite a bit when I was making exams or projects, thinking about assessments, that there are different levels of doing things, and the types of things like using the multiplication table or taking a derivative is at the lowest level of understanding, which is not to say that it's not important. The lowest level can be foundational, but it's not all there is. I co-author, I know I did not co-author, let me speak accurately. I mentored a student who wrote an article about chain rule, and she was an artist. So she was creating these images that were giving this very intuitive, easy to understand way of working on this calculus concept. And it was totally at the high level that is not, hey, can you apply this? But it was about creating something that led to deeper understanding or more insight. We don't have to go from the bottom up, and we don't have to go, there's no specific entry point that you have to come at this from. So if I were teaching this as my class, which I am not, I might ask students to create things well before they felt like they really understood them, because you can do that. You could ask someone, just create an equation, any equation, make it as complex as you want, and they don't necessarily have to be coming in with a background of lots of practice before they do that. But when I put these two things together, what I get is an emphasis on multiple representations and multiple approaches. That you have different representation systems: verbal, visual, graphical, numerical, symbolic, and you have multiple levels at which you can approach the activities. And when you put that together, there's just tons of different things you can do. RJ, I see you have your hand up. Please feel free to jump in.
I was just gonna say on the I'd done some work a long time ago in education technology, and some of it was on um, repetition based learning, and that move from okay, we're gonna just get this as a rote, you can remember this thing, to actually understanding it. There's something called the generation effect, which is like you contributing to your model of the thing, right? That is like, uh, uh, you know, trying to visually represent the idea, creating anything rather than just consuming. It's like they call it generation effect because it has this really significant impact on retention. So even if you weren't trying to build on the thing, but just trying to represent it in a different way has like this crazy impact on your understanding of it. And that it's uh, I think it's like the explanation for why it is like physical note taking has a greater impact than say like listening to a recorded lecture. Like you recorded the lecture in class and then afterward you listen to it. It's very different from in terms of retention impact than writing the notes as you go along. So it's interesting because like taxonomy represented as like this linear up and down, but you can kind of like go from jump to create and then come back down to evaluate and analyze. Anyway, it's just it made me think of that. Yeah.
I really like that. And I mean, it's how often are people able to apply things before they understand them? And they understand them through application, right? It's not like you have to jump in at one specific place and go up or down. It's that there are multiple different things you can do. So I kind of think of these like a pyramid. I put the rule of four at the base, and then I stack these sliced triangles on top of it, and end up with a mental model of a cognitive space that you can navigate as a way of working with mathematics. And so that might be helpful context for anyone watching this or coming to these meetings to understand why it might feel like we're jumping around, but we're trying to map in lots of different ways and create connections between these different things. I hope that makes sense. And that might give some context for looking at. So what I did in anticipation of this meeting, because I would not claim the title of expert about active inference. I've been familiar with it for I've been exposed to it for a little over a year, but I'm just now getting to a place where I have time to really focus on it. So I'm reading the textbook for the first time. And what I did was look through the chapter 2 and through the appendices to see what might be helpful. So maybe some of these things with a little bit of priming when we see them, if you haven't, totally fine if you haven't read them yet. RJ knows I'm like a very improvisational person. So when I was asked, what should we do before tomorrow? And I was thinking, that's a really, it'd be great if I thought about that, wouldn't it? The first thing I'm going to try to do is find the textbook, which I think I found a moment ago. But what I did was I went through the chapter 2 and the appendices to see both what the recommended mathematical background is and what the what is coming up like next week in terms of what we might be exposed to. So I thought we could walk through that a little bit with a particular emphasis on not here it is. Not the active inference per se, but what ideas are we going to see and what do those ideas mean and how might we be somewhat familiar with them. So what I saw in chapter 2, just to reality check myself, chapter 2 is the next thing that the group looks at, right? Or is it 2 chapters per, or 2 weeks per chapter? It's if someone is able to check that would be great. If not, super, and it's not a blocker, but anyway, let's talk about this, which is the first math equation that pops up in the textbook, and it's 2 fundamental rules of probability. Because probability is very important in this chapter as we talk about what is the certainty or the likelihood that something is true given the available evidence that we have. So this first rule of probability, quickly, to review what I always start with if I teach probability from foundations, is probability is a way of assigning numbers to things that could happen that give us an intuitive sense of how likely or unlikely something is. And probably anyone who comes to these sessions has at least some intuitive idea of probability, even if whether or not there's a formal definition. And many people will also have formal definitions. This first rule, the sum of all events probability, sum of the probability of all events has to equal 1, tells us something has to happen. And this concept, the name for this is the sum rule. But something has to happen. So we have a probability space, and we can divide that probability space, which is everything that could happen. We can divide that into events. And then each event has a probability. And if you take each of those distinct events and add them up, it has to be 1, it has to be 100%, because something has to happen. The other key observation that you can build off of is what's called the product rule. The notation, there's a lot of different types of notation that pop up here. So this probability of x comma y is called the joint distribution. And this is the joint probability, excuse me. And this is the probability that both x and y happen. You will see other notation for this. This could also be the probability of x and y. Some people like to use words instead of the comma. Or you might also see this as the probability. Some older texts use a symbol that looks like this. And I just realized how awful that looks when I type directly on white. So I'm going to move this over here. So there's the joint probability, which is the probability that we're interested in two things, and that this is the probability both of them happen. There's the marginal probability, which is the probability of one single event happening. And there's the conditional probability. So the marginal probability is just the probability of a single event. The joint probability is the probability of what's sometimes called a compound event, where two things are happening. And then there's the conditional probability, which is the probability that something happens given a specific piece of information. When you see P of xy or P of x or P of y with this divider between it, this is pronounced probability of y given x, which means I already know for sure that x has happened. And it's not hard for us to think of specific cases where if I know something has happened, it drastically changes my probability of something else happening. So these are the three different types of probability that show up in these rules. I think it's worth talking about them because, especially for people who aren't as deep in this, you're going to hear these three different adjectives, and it's good to recognize which is which. The other thing is we're looking at this from a Bayesian perspective, which means we think of probabilities as corresponding to beliefs. So probability is not a fact about the universe. A probability is a belief that we hold. And that's sort of the justification for why, if I know an additional piece of information, it can change my belief about the probability of another piece of information being true. I said a lot there, and I don't want to lecture the entire time, but does what I've said make sense here? I think these are three concepts worth highlighting. Cool. So we can look at resources about the difference between those things. And from here, there's these basics. When I say basic, I'm not saying easy. I'm saying fundamental, these different ideas about what you can do with these. From here, you can build product rule, the way that product rule and sum rule play together, which is marginalization. And you can also build various forms of Bayes rule. So if you look up Bayes rule on Wikipedia, which we might as well do, it'll look different ways. There are different forms that it can be written in. They all have the same justification. What I really like about probability is, unlike calculus, you can start with the few fundamental axioms of probability and really develop it in a logical way without needing too much time, too much space. So just starting with the two rules, the product rule and the sum rule, you can get to this Bayes theorem, which tells you a relationship between two different conditional probabilities and two different marginal probabilities. Already here you'll see the difference in notation for compound events. Like this definition of conditional probability is what the book is calling product rule, and already they're using the intersection sign instead of the comma. How is this useful? So I mean, there's the formula. You can practice using the formula. You can look at the visual proof or intuition about what it means. How is this useful? This is useful. The classic example is about testing for a disease. So the classic example here would be that you take a test for, let's say, cancer. It's a popular example, and it comes back positive. You know the false positive rate. There is a false positive rate. So you know the false positive and false negative rates of the test. What is the probability that you actually do have cancer, given that the test came back positive? This is a classic example of how to apply Bayes rule. I'm sure I can find an example online where they go through it in detail. And this is the type of calculation that shows up several times in this chapter, at least conceptually, where we observe something, which would be the test being positive, and then we want to update our information about the likelihood of something, which would be the disease. The way that this occurs is, so that's the big picture idea of what this box is getting at and why it might be useful. There's this terminology of prior and likelihood. And I like this example in the book of trying to determine whether you have an apple or a frog. The prior here is the prior belief that you have before you get additional information. So the prior would be before you take the test, how likely you think it is that you have the disease. And then the likelihood model is something, it would be about the test. It would be what you know about the relationship between the test results and actually having the disease. And I think the book does a fairly good job of illustrating this. Maybe it would be worth us doing some exercises or something at some point, but just for this high level overview that we're looking at and trying to maybe make it more comfortable, let's skip like calculations. I'll give you homework if you want it, but I don't want to just start there. And all of these calculations are using the rules in the box. So being familiar with the rules in the box are helpful to understand where these numbers actually come from. And the explanation is great. Then there's a notion of surprise. Surprise, I wasn't familiar with this unit, but after I read about it, it makes sense. Nats are like bits. They're the sort of continuous version of bits. Bits measure how much information, bits are a measurement of information that are expressed base 2, if you're familiar at all with that, because they're either 0 or 1. They're discrete. Binary and nats are the analog. They're just working base E. So nats are a different way of measuring how much information you get from something.
Oh, interesting. I did not know that term, nats.
And
I feel like it's in deep memory somewhere. Where does that come from?
it comes from natural log.
Oh, okay. I see. All right.
And the same way that bit comes from binary, right? And the thing
I
about
see.
is if you're working with a continuous probability distribution, or even if you're not, in like statistical thermodynamics, there's uncertainty, and it may make more sense on some of the physical things to measure information in a continuous way. And so the nat actually plays a role analogous to the bit. And you can convert between bits and nats just like you can convert between meters and feet, right? They're just different units. So nats are how you measure surprise, and surprise is how much information you get from a specific observation. And kind of a good place for us to wrap up is, where do we get to? Like, where we get to is that different probability models, different probability distributions will have different surprise statistics associated to them. And okay, let me back up. As there's a common mistake here, and I thought I would go ahead and make it. Actually, a few different notions of surprise that measure different things, and it's important to be careful about that. So one thing it's important to unpack two different notions of surprise. The first is the negative log evidence. I don't want to get caught up in the details here, but the idea is this notion of surprise tells you how unlikely something is. And there's a second notion called Bayesian surprise, which is actually about updating based on beliefs. So in other words, Bayesian surprise quantifies the difference between a prior, what we think, how likely we think something is before we see, and a posterior, how likely we think something is after it actually happens. And what that leads into is like the big math question, which is, if you wanted to quantify and say this probability distribution is like this one, or it is not, how would you do that? And it turns out there are lots of different ways to do that. and one of them is the Kullback-Leibler divergence. But the big picture on all of these things, because I'm not going to have time to go deep in the details, and it's not the purpose of this session anyway. What all of these tools are doing is trying to give measurement to information and measurement to likelihood of something happening or something being true. And the symbols and everything else are just supporting that and giving concrete ways to calculate it. And we can go deeper in the weeds if people want to. But when we talk about these things, we're talking about information and how much confidence we have something is true. And what this does is give us tools to measure that. Cool. So let's continue this in Discord. I'm happy to continue it, but I need to stop the sync session now. What I will say is I'm happy to give you homework if you want it, if people want to get their